Hello everyone, welcome back to Coding Champs. In today's video, we are going to be solving the problem lexicographically smallest equivalent string. In this problem, we are given with two strings of same length S1 and S2 and a string base string. We say S1 of I and S2 of I are equivalent characters. So for example, if S1 is ABC and S2 is CDE, then A equal to C, B equal to D and C equal to E. So the first character is equivalent to the first character in the second string, A equal to C. And then the second character in the first string is equivalent to second character in the second string. So we say P equal to D, and last character is also equivalent in both strings, C equal to E. Equivalent characters follow the usual rules of any equivalence relation. Reflexivity, A equal to A, and symmetry, A equal to B implies B equal to A, and transitivity, A equal to B and B equal to C implies A equal to C. Okay. So the equivalent characters follow these three rules. For example, given the equivalency information from S1, ABC and S2, CDE, ACD and AAB are equivalent strings of base string EED, and AAB is the lexicographically smallest equivalent of the base string. Okay. So return the lexicographically smallest equivalent of the base string by using the equivalency information from S1 and S2. Let's take a look at the examples. So firstly, we are given with S1 equal to PAR, KER and S2 equal to MORRIS, right? Now from the equivalency information, we know P equal to M and A equal to O and R equal to R and K equal to R, E equal to I and R equal to S. So P equal to M, A equal to O, R equal to R is by default. So let me remove this, and E equal to I and R equal to S. We can write this up here. So R equal to S. These three are equivalent, these two are equivalent, these two and these two are equivalent. Now, what is the base string given to us? Base string is PAR, parser, PAR. Now, we have P. P equal to M. What is the smallest? M. So, we write M here. And then we have A. A equal to O. What is the smallest? A. So, we write A here. Since we have to find the lexicographically smallest, at each position, we try to choose the smallest character. Okay. Here we have R. K, R, S are equivalent. So, what is the smallest? K, right? So, we take K. And then we have S. S also. S, R, K are similar. S, K is the smaller. So, we take S. And next is E equal to I. The smallest is E. So, we take E. And we again have R. S, R, K are similar. So, smallest is K, so we consider K. What is the lexicographically smallest equivalent string we can form for the base string? Is MAKKEK. So we return MAKKEK. Let us consider the second example. We have hello, then we have world. So we know H is equivalent to W and E is equivalent to O and L is equivalent to R and L is equivalent to L and O is equivalent to D. This is by default. We know for everything A equal to A. And next we have H equal to W, E equal to O, L equal to R and O equal to D. We can write this over here. Okay, now what is the base string given to us? HOLD, hold. And now for H equal to W. What is the smallest? Smallest is H. And then we have O. E, O, D are similar. So what is the smallest? E. So we write, what is the smallest is D, right? E, O, D, smallest is D. And then we have L. For L, we have L equal to R. What is the smallest? L itself. So we write L. And then we have D. D, O, E are similar. So what is the smallest? D. So the answer is HDLD. HDLD is the lexicographically smallest equivalent of the base string. Let us consider the next example. We have LeetCode and we have programs. So from this, we know L equal to P and E equal to R, E equal to O and T equal to G and C equal to R, O equal to A, and D equal to M, E equal to S. So E equal to R and E equal to O. So we can say E equal to R, R equal to O, and then we have T equal to G, C equal to R, O equal to A. So here we have O here. So we can remove this and we can write it over here. O equal to A, and then we have T equal to G, C equal to R, D equal to M, and then again E equal to S. E is present here as well. So we remove this and we write it over here. And we have C equal to R. R is here as well. So we remove this from here and we write C over here. And can we reduce anything else? L equal to P, T equal to G, D equal to M. They don't appear over here, so we cannot reduce it. So this is the final equivalent character. So what is the base string? Source code is the base string. So where is, yes, S is here. What is the least here? A. So we replace S with, in the position of S, we write A. And for O is here. So the smallest is A. So we again write A. And then we have U. Oh, where is U? U is not present in this. So we by default consider U equal to U. So we write U equal to U. And then we have R. R is here. So what is the smallest in this? A. So we write A. And then we have C. We have C here. C, these all characters are equivalent to C. In that, A is the smallest. So we write A, and E. E is over here. So in this, smallest is A. So we again write A. We have C. C is present here. So the smallest will be A again. And we have O now. O is here. In this, smallest again A. So we write A. And then we have D. D equivalent to M. The smallest is D. And then we have E. E is present here. So E equal to all these characters. So the smallest of them is A. So we write A. The lexicographically smallest string is this string. So we return this. So let's see how we can solve the problem. So let us consider the example. The first example, we are given with the string S1 as Parker and S2 as Morris. We know the strings S1 and S2 are equivalent. So the characters at the respective positions are also equivalent. So let us write them. P equal to M, A equal to 0, R equal to R, and K equal to R, E equal to I, and R equal to S. So let us consider them as the edges. Another point to observe is if P equal to M, M equal to P. If you want to form edge between P and M, it will be undirected. Okay. So let us form the edges. So we have edge from P to M, and then we have edge from A to O, and then we have edge from R to R. R to R is a self edge. So we know all by default or by the principle of reflexivity, we know every character is equivalent to its own. So we don't consider self edges here. And we have K to R, and we have E to I, and again we have R to S. So this is the graph formed from the from given equivalence. Okay. Now let me make this graph smaller. And what is the base string given? The base string given is parser. Let me write it over here. Now, what is the lexicographically smallest string equivalent to the base string? We have to find that. So for that, we iterate over the base string. So firstly, we have P. For P belongs to this component. In this component, we have to find the smallest character. So the smallest is M. So we write M here. And then we have A. For A belongs to this component, and lexicographically smallest character in that component is A only. So we write A. And then we have R. R belongs to this component. So lexicographically smallest in that component is K. So we write K over here. And then we have S. S again belongs to this component, and lexicographically smallest in that component is K. And Then we are here, E. At E, what is the lexicographically smallest at this component? It is E only, so we write E. And then we are at R. R belongs to this component. Lexicographically smallest is K. So the answer will be MAKKEK. This is the lexicographically smallest string equivalent to the base string. So how we can, what data structure or algorithm we can use? So this is like a graph, and these are all like components. So in the components we have to whenever we are, these are like queries. Whenever we are getting a character, we have to go to that component and we have to traverse the component. We have to find the lexicographically smallest character in that component. So we can perform DFS. Whenever we get a character, we perform a DFS on that respective component and we can get the lexicographically smallest string. This is one way of doing it. Or else we have another data structure known as union find. In union find, we have, for what we do, let us see, for each component we assign a leader. We union components. Using the union function, we make components, and using the find function, we find the parent or the leader in that component. So while making the components, we have a leader. In this problem, we can make the leader as the lexicographically smallest character. So if we consider this component, that we can make M as the leader since it's the smallest. In this component, we can make A as the leader, and in this component, we can make K as the leader, and in this component, we can make E as the leader. So we perform union on the given S1 and S2. So we perform union for M and K. We form edges between them, and while doing that, we make the leader as the lexicographically smallest string. And finally, we apply, whenever we get M, we apply find. We find the parent of P. So the parent of P in this component, the parent will be M. So we return M. In this way, we can solve this problem. So let us see how the union find works in this example. So initially we have, let's take the example hello world. For this, we have hello and we have world. So let me first write down the characters H, E, L, O, W, R, and D. So these are the unique characters. While we are writing code, we consider all the lowercase English characters, but for explanation part, I am considering only the unique characters present in our strings. And initially, all the characters are in their own components. And now we perform union operation between the similar characters. So H and W are similar. So let us perform union operation. While performing union operation, what we first do, we first find H and W. We find the parent of H. Initially, all of them are in their own components and all of them are leaders by themselves. So parent of H will be H itself, and parent of W is also W itself. So we form an edge between H and W. And what is the smallest thing? Smallest between H and W is H. So H becomes the leader and W goes into H's component. So let me erase the W from here. Next, we have E and O. E and O, this parent of E is E, parent of O is O. So form edge between E and O. The smallest is E. So E will be the leader and O will be in its component. Okay. Next we have, let me erase O from here. And next we have L and R. So L and R, parent of L is L, parent of R is R. We form edge between L and R, and the smallest is L. So L will be the leader and R comes into its component. We form an edge between them. Erase the R. Erase this. Okay. Next, we form an edge between R and R. R is the parent of itself, so we do not form the self edges. So we leave it and we next move to O and D. Between O and D, O's parent is E and D's parent is D itself. We form an edge between E and D. What is the smallest? D is the smallest. So now D becomes the leader of entire component. So we have, let me write D over here, and me erase this, and E will be a normal. We form an edge between E and F, and what is the leader? Leader is D. So we have completed forming we completed forming unions between all the similar components. Next, what we have to do for base string, we have to find the lexicographically smallest. So the base string is whole, and we have to find lexicographically smallest equivalent string for the base string. For H, we have to find the leader of um, we have to find the leader of H or the parent of H. For H, it is parent of itself. So we write H only. For O, we have to find the leader or the parent. So the leader of this component is D. So we write D. And we have L. The parent of or the leader of L component is L itself. And we have D. And the leader of the parent of D component is D itself. So we write D. This is the lexicographically smallest string. So we return it. This is how we can solve the problem using union find. Let us look at the code. In union find, we basically should have a leader array. So let's have a leader array. New integer of 26. And initially, each leader should point to itself. So let us make a loop. And each character should point to itself. Here I am taking integer of 26 because in the problem we are given that the string consists only of lowercase English characters. So we map A to 0, B to 1, etc. And initially all the characters will map to themselves. And now let's implement the union function. Private void union int x int y. Here we are considering the characters as integers A to 0, B to 1, etc. So on that. And now for x, we find the leader of x. Find leader of x. And we also find the leader of y. Find leader of y. And if both of them are equal, if leader of x is equal to leader of y, then we just do nothing and we return. Else, if leader of x is less than leader of y, in that case, we make x leader as leader to y vice leader also. So leader of y will become leader of x. In this way, we make the smallest as the leader. If else, if y is greater, then we make y as the leader to x component. So leader of x will become leader of y. So this is the union operation. Let's implement the find parent function. Find parent returns the integer and find leader. It takes integer x. If x is equal to leader of x, then x is the leader of the entire component. So we return x, else we return find leader of leader x. So we find the leader of x's leader. Okay. We make, if you know path compression in union find, we make leader of x equal to find leader to compress the path. And what now we have implemented union and find operations. What we have to do next, we iterate over the strings I equal to 0 and I less than s1 dot length, both of them are of equal length, I plus plus, and now we apply union operation on the similar character. So p is similar to m, so we apply union function on p comma m. So s1 dot character at I, and we have to pass integers, so we subtract a, and s2 dot character at I, do same thing here as well. Now we perform union operation on all the similar characters and have formed the components. Next thing is we have to find the lexicographically smallest string similar to the base string. So string, and let's say it as result, and initialize with empty string. Now we traverse through the base string character, base string. Let's convert it to character array, and now result plus equal to, we have, let's find the leader for the character. We have to pass the integer, so we subtract a, it returns an integer, so we again have to convert the integer to character, so plus a, and we have to convert this integer to character, so character, opening this. Finally we return the result. Looks good. Let us run it. Integer array. Let's run it now. Oh, this is small y. It passed all the sample test cases. Let us submit it. It got accepted. So what are we basically doing here? We are using union find to solve this problem. Firstly, we union all the similar characters, and we then go through the base string and we find the leaders of the components. The leaders of the components are basically the smallest characters present in that component. So we find the smallest component and we add it to our result string and we return the result string. I hope you understood the problem and the solution. There goes a lot of time and effort in making these videos for you. So if you did understand the solution, make sure you hit that like button. And for more daily videos, do subscribe to Coding Charms YouTube channel. Keep practicing. See you all in my tomorrow's video. Till then, take care. Bye-bye.